Okay, dear students, let us now discuss derivation to find out moment of inertia for a lamina. So, in this particular case, we will be discussing about a rectangular lamina. But the case that we will be discussing here, we can generalize later on for a variety of figures. But right now, we will be just focusing on this rectangular lamina only. Just like in the previous video, we discussed about the center of gravity of a cone as a general case and to understand the procedure. Okay, so let there be this be a lamina which is shown in this figure 5.9, and it is having a thickness of b, and that is, or you can call it as a breadth b, and depth of d. Okay, and there are two axes, which is one is passing through its CG along the x-axis, and the other is passing through its CG along the y-axis. That is, they are being shown as x and y respectively. Okay, so let us have a small element of thickness dy at a distance of y from the x-axis that you are seeing over here as a shown with the these lines, okay, hashed lines. Okay, now we can easily find out the moment of inertia. First of all, we can find out this area, and from area you can find out the moment of inertia about x axis. Okay, this dot which is indicated with the dotted lines. So the area is b into dy. Area is because b is the breadth and dy is the thickness for this small element. Okay, and the moment of inertia of the elemental component about the x this axis, middle axis, is area into y square, because y is the lamina's distance from this axis, central axis. Okay, so now you can integrate this terms that we obtain here, that is by square into dy over the domain, starting from y is equal to 0 to y is equal to d by 2, because this is d by 2. This will give us the moment of area of this complete lamina. Okay, so by square into dy, which will be equal to twice of that, because you have the upper part of it and the lower part. So twice 2 comes outside, and this is the integration between 0 to d by 2. Okay, and this comes out to be bd cube by 12. This is the same thing that we discussed in the first table. Okay, and here we have discussed about the derivation. Okay, and similarly, the moment of inertia about the central axis y, which is given over here. So this will be equal to the dv cube, because in this case d becomes its horizontal axis. You can assume that to be a horizontal axis or equivalent to the horizontal axis, and b becomes its total thickness. Okay, so this will be equal to dv cube by 12. Okay, um, uh, uh, okay, so there is another corollary of this discussion that we had. Suppose you want to find out the moment of inertia about axis LL. Okay, now here we will apply the theorem of parallel axis. Okay, so we already know the moment of inertia of this, okay, figure about axis xx, which is passing through the center of gravity. So we will simply say that this moment of inertia about LL is equal to LXX plus A into h square. So area we already know it is B into D, and H is the distance, this distance of the CG from this line LL, which is nothing but D by 2. So we already know the moment of inertia about its centroidal axis, which is BD cube by 12, and using the theorem of parallel axis, you can find out ILL is equal to this moment of inertia plus BD into D by 2 square. So this is comes out to be BD cube by 3. And similarly, the moment of inertia about the axis MMM is dB cube by 3. Okay, and if you are interested to find out the moment of inertia about the z axis, okay, which is passing through the centroid, then you can simply sum those moment of inertia about xx and yy, and you can find out that. Okay, so this is about the moment of inertia derivation for a simple figure, and this procedure that we discussed over here you can apply for uh, variety of figures or sections. And though after these derivations only, the table that I discussed where we said that for a circle it is pi d cube, sorry, pi d raised to power 4 divided by 64. This is the derivation which we found using this procedure.